Hello everybody. My name is Mikhail Svetkin, and today we are going to talk about coroutines. We are going to talk a lot about them and how they look inside, and how hard it is to write them. So there will be a lot of code. So please be with me. It could be hard, but I will try to explain everything step by step. So my plan is to first start to explain what is the coroutines. Then we'll take a look under the hood, how they looks like, and then we will talk about how to use them. And I want to start with first of all, I want to start with the overview of C++20 coroutine support, because we got it in only there. So right now it's supported by 3 major compilers. GCC supported from version 10. MSVC supported it early, but I tested only on the latest, so I'm not sure how good it was before. And the Clang supported from the 8th version. It's still under the experimental branch namespace, but works okay. So I don't know why it's still there. Yeah. From the language, we are getting 3 new keywords. So it's a coroutine, coroutine, and coroutine. And from the library, standard library, we get few types, not a lot of them. And we will go through most of them to explain what they do. By looking at this small support, what we've got should be obviously say that it should be probably easy to write the coroutines, because not so many things. But yeah. Before we go next, I just want to put some motivation for us, because we need to understand how we can use them. And let's say I heard a myth that coroutines helps to write the synchronous code. And this is our statement, which we want to prove today. And by proving it today, we will take this piece of code. So I'm quite sure by looking at this, you're like, what this code is doing? Because despite the fact this is just 15 lines, it's hard to understand what it does. It could be the reason because my code style, which I choose, is completely terrible. That's the first option. Second option is that the code is bad written. That's also an option. And the third one is that it's just hard to write the synchronous code without the proper tools. So if you still don't understand what it does, that's okay, that's fine. We will just go quickly through it, just you will understand. So we have a function, some worker, it accepts the socket and the data. Then we start some long computation task, and we don't want to block the main thread, so we kind of use the executor to start something and get the future. Then we do some fast computation. Then we say they want to send this temporary result to our socket. Then we set up a callback, which is supposed to say when we send the data, we would be ready to receive the data. And we again set up the callback. And when this data arrived, we will get the result from the future, take the data which we got as a response, and do some processing and send it back. So as I said, code is terrible, hard to understand. I understand it. It probably not compile because I did some mistakes while I was writing it. But could be. So just keep that. Don't keep it in mind. No, we will come back to that. We'll rewrite it with the coroutines, and I'm quite sure we'll see something. What's the difference between two approaches? So first, let's start with this theory. What are the coroutines? And when I Google it, the first answer which I get is that the coroutines are generalized subroutines. And the subroutines is the sequence of program instructions that perform a specific task. Basically, it's a functions. We all know them. Yeah. The main difference between the coroutine and the subroutine is that coroutines could be suspended and resumed. And that's the main difference. And when I say it, it's probably not easy to understand what it is and how it works. But we will get to it. In C++, a function is a coroutine if it contains one of the keywords, coroutine, coroutine, or coroutine. So let's try to write a coroutine. No, sorry. Before we go, I just want to highlight some steps of invocation, because I think it should be important to know. So let's take a look at these 2 simple functions. We have a function main, which call foo. Foo does some computation, and return. So I would say that in normal functions or subroutines, there are a few stages. Like first is invocation. This is the step where the compiler generates some code to actually allocate the stack for the local variables, remember where to go back, and so on. So there is this process, then there is execution of the body, and then there is return control to the main and the value. So in the coroutines, the same thing, except you can suspend and resume the body multiple times. And we will try to do it right now. So let's try to write our first coroutine. We know that we need to use one of the keywords. Let's start with simple one. So let's say that we want to change the return to say coroutine. Great, we've done it, super simple. And I think maybe it works. Let's try to compile it. And surprisingly, when we compile, we get an error, unable to find the promise type for this coroutine. And if we just go back to the slide where I said about the coroutine support, there is something about promise here, no coroutine handle promise. But that's not what we're actually looking for. So we need to go to the Google. So I Googled it, coroutine promise type. And I found that there is a link to the CPP reference. And when I go there, I found that there is something about promise, something about how it's executed. And actually, I didn't understand what to do with that. I would be honest. So I went back, I found this link, and I read it, then go back, I read this one. And after that, I started to see the picture. So it turns out that each coroutine should return a specific coroutine type, which follow the interface. It should contain the promise type, and this promise type should implement 5 functions. It should implement the get return, initial suspend, final suspend, unhandle exception, and return value or return void. Depends what you want to return from your function. It's either value or it's a void. So one of them. And then you also can see that initial suspend and final suspend, they actually return some awaiter type. What is that? I don't know. So it turns out that the awaiter type is also a specific interface. This interface tells the compiler how to basically await, how to generate code which will eventually do our awaiting mechanism. So on this one follows, you need to implement 3 methods. Await ready, you tells your await system your expression is ready. Then if it's not, you will call await suspend. And there is 3 different versions of them. So if you need to implement only one, it depends which one you choose, the behavior would be different. And then you need to tell how do you want to get the data back from the await expression. But if you still doesn't understand how it works, that's quite fine. So I didn't understand it either at the beginning. So what we do is I will just summarize some things which we need to remember. So the promise type defines and controls the behavior of coroutine. The awaiter type defines and controls the await behavior. Good. Steady coroutine traits. This is a specific traits which used by compiler to get the promise type from the return type of your coroutine and generate some code for you. Basically, what it does is something like this. It's take the body of the coroutine function, transform it, and do some other things. But don't worry, we will take a look everything in detail here. So okay, let's write our first coroutine. And I call it Taskind. Normally in any other presentations or libraries, you will see that there is a generic name task. And in my case, I don't want to make anything generic, just super simple. So it's called Taskind because we work with the ints and return ints. So let's try to write it. So we have a Taskind. We define the promise type. The promise type have an empty constructor, just in case. And the next thing which we need to implement is get return object. This function is used by compiler to understand how do you want to construct your coroutine. And in our case, we want to construct it with the basically coroutine handle. A steady coroutine handle is our interface to actually control the coroutine. So for that, we need to implement the constructor, which accepts the handle. And you see that I don't move it. I don't just assign it because the coroutine handle inside it just like a pointer. So it's perfectly fine just to assign it like that. We need to store it. We'll use it later. And the next thing is that we need to implement as initial suspend function. This is the first suspension point which we need to implement to tell the compiler how we want to suspend. And as of now, I return a std suspend never. There are 2 things in a std library which we can use. One of them is 2 awaiters. One of them suspend never, and second one is suspend always. Guess by the name, suspend never means don't suspend. Okay, so let's just do that. The next one, we need to decide what we will do in the end of the invocation of our coroutine. Let's say nothing, we just don't want to suspend. Then we need to define what if the exception happens inside the coroutine, how to handle it. So you need to implement this function. And as of now, you see we are exception free. We decided we don't want exception, we don't want to handle it right now. Then since our function, which we saw before, is returning the int, we need to capture that result. And the way how the coroutine works is that the coreturn statement the expression of it will be passed to the return value. So we need to keep it and store it. So we store it as just a promise member. And then we need some interface how to get that result. And we use the std coroutine handle, which can get us a pointer for us, or promise, and then we can get the value. So far, so good. So let's try to use it. We go back to our code. We go to the function declaration, and we change int to be a Taskind. We don't change anything in the body. That's the same. Then we go to our main function. Now, since we return the Taskind, we don't return int anymore. So we have to change the type. So let's say after task. The next thing is that we need to retrieve the result. And we have this function called result. So let's call it task result. Okay. So let's try to compile it and see. And as you see, the result will be okay. We get the result. I think the calculation which I did is correct. It's 110. So here we are. We wrote the coroutine. That was painful a little bit. And what do we actually get? We didn't get anything. We just call the function, get something, doesn't help. What was the reason for that? So let's try to actually use the feature of the coroutine, try to suspend a coroutine. Okay? So we will go back to our task int. We go to the initial suspend point. And let's say, okay, let's suspend it by default in the beginning. And you might ask, why do we actually need it? And the reason is that imagine that our foo, right now it's very simple, but it could compute some heavy things, which takes a long time. So before we actually resume the coroutine to do something, we want to suspend it and then maybe move it to another thread or something else. So that's might be the reason. So let's say we want to suspend it by default, and we can do it by just changing the return type to be suspend always. This is a second awaiter type which provided by the standard library. And let's see how it works. So now, if we run it and compile, the result will be -1. This is a default value which we got from the promise type, which we initialize with -1. It turns out our functions didn't work. It's probably as we expected. We suspended it and we never executed. So the way, if we actually want to now to get the result, we need to resume the coroutine by doing it manually. So we need to implement the resume function. And that's pretty simple. We just need to use the std coroutine handle, just say resume, and that should work. So if we compile, now we get the result. Beautiful. But just to be clear, to understand what's actually happened right now, let's look at the call graph. So the main function invoke the foo. Foo hits the initial suspend point, and we know that we said that we want to suspend. It immediately returns the control to the main. And then we call resume it manually. And then we will go back. We resume the foo. It hits the final suspend point. We know that we don't want to do anything here. And we return. And we obtain our result. Great. And if you see, I just run it again, we get the result. However, this code has a problem right now. We wrote it, it's supposed to be good, but it doesn't work. For some reason print the result, but actually we got the undefined behavior here. The reason why it's undefined behavior is because the coroutine handle internally works like that. If you reach the final step of the coroutine and you pass the final suspend, it will immediately remove the coroutine internally. And we didn't catch that moment. So now when we actually call the task result to get the result, we actually call getting result from the handler which was removed. So it seems for some reason it still works. So let's try to fix it. So we will go back to our final suspend point. since we know that if we don't suspend it, and then the result would be that the coroutine handle would be destroyed, we need to actually suspend. So let's do it. We just use the suspend always. And let's try to compile and run. The result as it used to be, correct. It looks great. We don't have any undefined behavior, you can trust me. But if you run the valgrind, turns out that we have a problem. We have a memory leak. How did this happen? It's not supposed to be. And it turns out that, so the coroutine handle is kind of right thing and kind of smart pointer in the same time. But if you don't follow the entire path of the execution of the coroutine, you have to actually delete it manually. So in this case, we just need to implement the destructor, which will call the destroy, the standard function, and yeah, destroy the coroutine. Painful, but okay. So I think we finally wrote a first coroutine which is supposed to work without any problems, and I congratulate you. So I think we unlocked some achievement. We wrote the first coroutine. Just want to summarize it a little bit because there will be a lot of knowledge after that. So coroutine must return a coroutine interface type. You have to implement it. There is nothing that standard gives you. So the promise type controls the coroutine behavior. That means we can decide, do we want to suspend? Do we decide that we want to resume? How to do that, how to handle exception, how to store return type. And yeah, so that example was very simple. Our Taskind is very, very simple coroutine. So in reality, you will need something more generic, something like this. And I reference here Ecor or whatever. It's my small tiny library which I wrote just to try to understand how the coroutine works. So in reality, you can make it template based. So you can actually specify the type, and you can generally use this task class to return something from the coroutine. And also inside this class, we will not go inside that class because it contains many details, because you want to avoid extra copies, you want to make sure that everything is movable and so on, that the exceptions handles properly. So we just will not go. I just want to show you that we can do something, but you need to do it manually. Nobody will give it for you. So, okay, great. Now we learn how to suspend the coroutine in the beginning and the end. Let's try to suspend it somewhere in the middle. So let's just inject this line, which is a call wait std suspend always. That's first our usage of this new call wait operator, which is accepts the call wait expression, and in simple way, I think that you should follow this awaiter type. And what it does is just suspend. If the awaiter type tells suspend, it will suspend. So now if we run it, we will get the result -1 again. We didn't reach the core return. We didn't reach the final suspend point. So how do we fix it? 1 second. Yeah, before we fix it, I will just show you the graph what happens. Sorry. So the main function invoke the foo hits the initial suspend, it returns the control, we resume it once. We hit the suspend always, we return the control, and the way how to fix it, we need to resume it again, manually. Great. Then we will hit the core return, and return will do a return for us. Nice. Now if we compile, we get the result. That's great. However, the problem is that if we look at this manual resumes which we do, is that actually we don't know from the main function how many suspension point foo has. So we need something to be able to understand, do we need resume more or just continue our execution? So we can do it by implementing the done function. It's basically called the handle done, which tells us done will return true only if we hit the final suspend point, otherwise it will return false. So until we hit the final suspend point, we can resume again and again and again and again. So nice. Nothing else we can do here, just resume. Yeah, okay. So now we know how to resume, we know how to suspend, but let's try to be a little bit. Let's try to understand how that magic actually works, because we know that there is some magic around, because some words, some generation, and so on. So I suggest you to be with me on a journey to be a compiler right now and try to implement to make the compiler work. So I will start with these simple lines that the compiler, wherever it sees the coroutine, it's actually generate a class for you. You're not able to get it, but it's there. It uses the std coroutine traits to take the promise type from your Taskind and put it inside as a promise. Then what it does is that it will analyze your function declaration and generate the same constructor for the coroutine handle. It will accept the same arguments which you pass to the function, and it will store it on a local stack. Here we works with the ints, so the stack is pretty simple. I just implemented, but in reality that should be something which contains any types. So it's just some pseudocode here. So yeah, it put it on a stack. Great. Remember that make a reference for us that we can use that variable. Yeah. So the next thing is that the compiler will try to analyze our function. And it says, okay, we have a first line. Let's create a step for us. It will take the line, just copy paste it actually. Great. Then it will see that there is a suspension point. It means if we suspend right now, we will lose the result of the result 1. So what we need to do, we need to save it on a stack. So it will just push it like this. Great. Then it knows, it will start to look what will happen after the suspension point. It will start to generate a step 2 for us. And it will again just copy paste the line, the same as it was in a step 1. Now, however, it knows that we reached the coroutine statement. We don't really need to save anything. We just need to put this to the promise that we can retrieve the value. Great. Yeah. So now if we take a look at what happens when we hit the resume. The resume function is pretty simple actually. What the compiler does, it's actually have a step pointer to the function call. I'm saying compiler, but it might be an implementation different, but we just try to be a compiler here. So it keeps the pointer to the step. By default, step 1. Then in each, in the end of each step, it will just assign a pointer to the next one. So when we call resume first time, we call the step 1, and then we say that the next step should be step 2. When we call the resume second time, it will say step 2. Invoke the step 2, and the step will be null pointer. And as you see, if you call resume next time, it will be again undefined behavior. This is the same as in a standard right now. Great. Very nice. We've almost done the compiler job. So let's now take a look how the invocation of the foo is changing, because somebody should create this coroutine handle foo object for us. Yes. So I would say the compiler might just guess here. I don't know certainly. What it does is actually expand it to be a lambda, which returns our Taskind. It allocates on the heap coroutine handle foo, pass the variables, arguments, get the promise, construct the return type, invoke foo, and return task. So if we look right now at the foo, it also does something here. So what it does is it's completely kind of rewrite it. First of all, it says always in line, because it doesn't make sense to be this as a separate function, but just don't want to put it in one piece. Yeah. So it's wrapped the function body, and it add this initial and final suspend points. It also put the try catch, and then it's called resume. That's how it was. So in our case, we hit the initial suspend point, we return the control back to the main called resume, and so on. So that's how it looks from the compiler perspective. And if you think about it, it's kind of similar to lambdas, because we know the lambda is very nice syntax, but in the end, it's actually a hidden class generated for us. So the same approach is here, just a little bit more thing. But yeah. So I think we've done a pretty good job, and I think we again unlocked the achievement. So I think as a compiler. And just to some summary here, that the coroutine frame allocated on heap, so there is allocation. You cannot remove it. The one thing is to say is that you actually can provide your own custom allocator by implementing the new operator for the promise type. So you can do some smart things here if you want. So the coroutine is stackless. So each coroutine actually contains their own stack internally. And coroutine can be suspended and resumed multiple times. That's what we saw. Yeah. The next step in our journey is actually try to call a coroutine will call a coroutine. So imagine that we have a function bar, which just do some calculation. And then let's imagine that we want to call it and replace line 7 to be the call of this bar. So we'll call bar, we'll get the task. We know that our Taskind is by default suspended. So let's resume it. And then we need to rewrite a little bit co-return to be task result. Now if we try to compile, we get the different result because the math is different, but still it works great. But I think if you look at this code, that doesn't look great. If all the time when we use the coroutines, we have to write this thing, get the task, resume. We don't know how many suspend points there. It's just nightmare. But luckily, we have a cure for that. We can write it like this. We can use the call wait operator here to actually say that we want to call this coroutine, await until it's ready, and get the result. There is only one slightly problem that it doesn't work out of the box. Of course, we implement our coroutine and we need to implement the support for the call wait, because the call wait works with the awaiter type and it doesn't know anything about Taskind. So the way how we can fix it is that we need to implement the new operator called call wait. This is also something new in C++20. So here you have to implement the awaiter, which in our particular case right now, I just implemented just proof of concept here. It's accept the handle. We will use it later. And we need to define these 3 methods. First of all is await ready. We need to tell the await mechanism is our expression is ready, our coroutine is ready. So we can use it to say handle done, is it ready or not? Then if it's not ready, the coroutine mechanism internally will try to suspend. So we need to implement this behavior, what we want to do on suspend, and we will implement the await suspend function in the way that it returns the coroutine handle. And that function declaration, the way how it is, if you return the coroutine handle, the await mechanism will just resume it. So in our case, we will just resume the current coroutine, which is a bar coroutine. And then we just need to explain the compiler how to get the result. And here is the same, we just handle promise and get the result. So now, if we try to compile and run, it turns out that we get the -1. It doesn't work. But there is no mistake, to be honest, in the code, except the logical. So let's see in the call graph how that works. So again, the main function invoke foo, we hit the initial suspend, we return, and then we hit the resume first time. That actually triggers to invoke the bar. Bar hits the initial suspend and returns control back to the foo. Then we call wait mechanism internally, call the await resume just to understand what to do next. And then it resumes the bar coroutine. However, in the end, something goes wrong because the final suspend now actually return control to the main. It just bypass our foo. And yeah, we need to fix that. And the way how we can fix it is that we go back to our call wait implementation. You see that await suspend actually accepts one argument, which is a handle to the awaiting coroutine. In our case, it's a foo. So what we could do is we could remember this. We can store it inside our promise that by the end, we want to continue execution of this coroutine, of the coroutine foo. So we just keep it in the promise. And I will not write the code for this simple function. But however, now we need to say what we actually want to resume in the end. For that reason, we go back to our promise type. We need to rewrite the final suspend point. Again, we will define some final awaiter, which is always say that the await expression is not ready. And when we hit the await suspend, when the suspend mechanism and await mechanism try to ask what to do next, we will return what we remembered to do. Great. And now if we try to compile it and look at the call graph, now that works. We get the right result. So in the same thing happens, just the final suspend will actually resume the foo, and foo will hit the coreturn and go back. Great. That was a little bit hard to do, but we managed it. So let's just summarize it, and I think we get the achievement. So awaiter type controls the await behavior. Awaiter type is a glue mechanism for the coroutine, so you can decide what you want to do, what to execute next, or maybe not execute. And the call wait suspend the coroutine, but it also a mechanism to retrieve the result. So very useful thing. Okay, let's go next. And the thing is, since we can use this call wait, maybe we can rewrite the main function to also use the call wait to be like that. And let's try to compile it. Surprisingly, cannot do that. It specifically say cannot be used in the main function. Actually, I went to the standard to read, and actually it turns out there is a specific paragraph say you cannot use it. But let's try to trick the compiler. Maybe we can create a boo function and call it. Maybe that works. Unfortunately, it doesn't. It turns out that you can use this call wait, call return, or call out, which we don't talk to today, is that you can use it only in the coroutine context. So to be able to make the asynchronous code and synchronous code to be friendly to each other, you have to invent something, or just call this manually resume blah blah blah, which makes your code uglier. Yeah, and what we can do is we can implement some primitive. In most of the libraries, it's called SyncWeight. Same, I called it in my library. So what it does, it's internally it does this magic for you. It checks, do we need to resume it or we need to wait? So it's a synchronous blocking call. We will wait until the coroutine is ready. They continue only after that. Yeah. So that was the coroutine summary. Now I tell you that you are masters of the coroutine. You can go and write it. Just remember this thing that you need to implement the coroutine interface type. Remember that the promise controls the behavior. If you do it wrongly, something can go wrong. Then you need awaiter types. Awaiter type which controls the await behavior. We know that coroutine is allocated on heap. So if you're embedded developer, you don't have a new, then you need to write it. Coroutine is a stackless. Coroutine can be suspended or resumed multiple times. And I said this, and the next thing is that compiler doesn't care what to resume. It's more like runtime decision here, wherever. He will do wherever you say. So, and the most important, that the coroutine behavior depends on developer implementation. So you don't know how it works. You can see the documentation and yeah. So let's try to use it. Now we know everything. So let's go back to our code, which was maybe you forgot it. Maybe you don't remember what it does anymore. Let's try to rewrite it. So we still have the same function definition here, unaccepted, and then now our executor will return a task instead of a future. Then the fast computation is the same, and this is the first place when the code looks better. So now we don't need to set up a callback. We can just say call wait socket send, and we will await until the send operation is completed, and we will continue our execution after that. Yeah. So the next thing is what we can do is rewrite our socket read the same way. We don't need a callback anymore. We can just await when it's finished, which is nice. Now we can call the process function, and we again can just await the result of our task and pass the data which we read from the socket. However, some of you can think, okay, that doesn't look great. We again have a temporary variable. Maybe we want to simplify it to be it like that. And interesting thing happens is that we tried to avoid the temporary variables, but we accidentally broke the function behavior, because C++ doesn't guarantee the evaluation order, and if it does, I made a mistake in the code. So what happens is here is that first of all, there could be two situations. First, we start to await the task, and the second, we await the read. Or other way around, we can start to wait read, and then we can start await the task. So that doesn't work well. And it's also raises a question as actually, how do we initiate two asynchronous operation and wait the result? And again, there is no any solution from the standard here. What you could do, you just need to implement a helper function, which called when all. What it does, it just take your awaitable objects, combine them together, and return a tuple for you. Then you can use a std apply to actually pass this tuple to the function. So that's the trick here. So the last thing is just to send the final data. I think we get, the final thing is to send the data, and I think so far, if you look at the code, I think it looks better from my point of view. I think you can agree, at least it's easy to read. Maybe not that familiar, but still easy to read. So I think the myth is correct. The coroutine helps to write the synchronous code. It's more readable and simple. However, there are problems. So if we take a look at this code more precisely in the new code, it turns out that it doesn't work actually. It doesn't work for the two reasons. First of all, somebody have to go and implement the asynchronous API for the executor, for the socket. Imagine that you've done it. Then the problem is that our onAccepted still returns void. That means we're not able to use the call wait because it's not a coroutine context. You can say, we wrote the task, we can use it. Yes, sure, we can. The problem is who is going to handle this task on the top level. And then who is going to handle it on the top level of that top level. And you need to go up, 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 up in your stack. You're not going to write your code in one day. So there should be a solution how to fix it. I have some ideas. I'm not saying they are great, but I just have them, so I will just share with you. So what we can do is we can create a Lambda. This Lambda is a wrapper for us. What it does is just a thing to create this task for us locally and resume it. I think the code becomes a little bit more difficult. Yes, that's true, but still we get this nice syntax. So maybe that worth it. The problem is that that code still doesn't work. And there is a few problems. First of all, the Lambda captures. We all get used to use them. The problem, they don't work with the coroutines. Coroutines, Lambdas and coroutines has a different lifetime, and the coroutines save on the Lambda arguments on their stack. They ignore completely their capture. So you cannot use the capture if you want to use this approach. So what you have to do, you have to create all the three arguments and pass it like this. That could be still okay-ish. The second problem is that we call the task resume on the line 14. It resumes the coroutine. It hits the first call wait. Then it returns the control to the onAccepted. And then we destroy the task. But if you remember, the task has a destructor inside. So it will actually destroy the coroutine. So we need to do something here. And this is the best thing which I end up in my example, but maybe you have better suggestions. So you will have to keep your tasks inside. So you can push it and then somehow clean up it. You need to maintain it. So not the best thing, but at least I would say a workaround. So yeah, maybe you will end up to making some, I don't know, the base collector or something, but you will need to do something. And unfortunately, there is no good answer how to do it. We need to solve it by ourselves in each project manually right now. So I think that's a problem. So how to actually use the coroutines? You have to implement everything. You have to implement the base coroutine types. Let's imagine that you've done it. Then we didn't even talk about the concurrency here. Yes, we don't create any threads and anything. We didn't try to execute our coroutine on the different thread. But imagine that we do. Then we lack of the primitives for synchronization, because we cannot use anymore std mutex, std semaphores. We cannot use std conditional variable because they're all blocking. And that's unfortunately, so you have to implement them as well if you want to have multi-threading code. Then second question is how to communicate between two coroutines. In the languages like Go, you have channels in the standard library, and you can just use it. In our case, again, we don't have anything. Then we need the tools for integration, synchronous code and asynchronous code, as I show you. We need like SyncWeight, for example, or actually how to keep the task alive and so on. The last thing is, or not last thing, but one of the important thing is that you actually need to implement the synchronous API in your project. So it means every class which is supposed to be available in your coroutine context and use the core weight, you need to go and duplicate that API. That's costly, but we cannot do anything. And most of the languages, the way how they solve it, they just have two APIs. So we have to do the same, unfortunately. And then there is integration with an event loop, because, for example, if you use, for example, Qt or you use Boost IO server, you have to integrate it. The std-asio, I think they have the support, but maybe you want to have a different behavior, so then you have to actually integrate it by yourself. So, and as you can see, there are many things to do, and not all of them are easy. So I can just say you good luck with doing this. I can just tell a little bit about my story, because when I decided to learn the coroutines, I had to actually implement a small library, because otherwise it didn't work. So I implemented this eCoro coroutine. It's a pretty small project with just few primitives and just want to play around to see how it works. I implemented not just quite few, and it managed me to build this presentation. I just want to highlight the two of the most important thing is that if you have a task, generic one, and if you have a task promise, like this base promise class, then you actually can implement the rest of the things. And that's how everything inside of my library works. I just reuse this task and task promise to implement SyncWeight, when all, and the other stuff. So if at least we have this in a standard, maybe our life becomes easier. Maybe. And just in the end, I want to show you some awesome example which I wrote with my small library. So I implemented the scheduler. It's a single threaded, so it just like this. And these schedulers spawn 3 coroutines. One of them is just awaiting the sigint. The second one in the infinite loop just sleeps for 1 second and print it. The third one does the same, just sleep for the 10 seconds. And surprisingly, it works. No errors, no mistakes here. I didn't get any crashes so far. But the thing is that to be able to write this example, it took for me some time. I cannot say exactly because I did it as a fun project, so it takes some time. So, and I think one of the complicated thing was there is that you have all these pieces. You can build a task and then how to go and integrate it, and it was kind of hard to grasp. Build a nice API. There are libraries outside on GitHub. You can find them, but I think they all solve their own purpose. They all solve their own needs. And I think we are lacking of something more generic, something that we all can use. And I'm not saying that my library is the cure here. I'm just saying that I tried to research something. Yeah, I just want to show this awesome example because I was super happy when it works. Yeah. So that's all. I was a little bit fast, I think. I was a little bit nervous. You can see it. So yeah, thank you all, everybody. And yeah, do you have any questions?
Well, the async keyword has been there for many years now in C++, so I wonder why should I use this that just came out? What is the big benefit over just using async?
STD async is using the threads. Yes, and you cannot control it. You don't know how many threads you allocated. You don't know. That's a completely different story here. This is not about kind of it's just a mechanism for you to create something. You want to execute it somewhere else, but the async will create you a thread. Sometimes you don't want a thread, so it's a little bit different concepts. And the words, of course, are misleading because now we have this asynchronous stuff and a steady async that doesn't. Yeah. Any other questions? Everybody is going to write coroutines today? Or, yeah, tomorrow. Okay, if there is no any question, then just ask me if you find me there. Yeah.